Hello, everyone, and welcome to the Mindscape podcast. I'm your host, Sean Carroll. We talk a lot about science on this podcast, and science has very lofty goals. We try to understand the fundamental workings of nature, whether at its broadest scales, its tiniest scales, or somewhere in between. But science is also part of human life, which means that there are things like politics and human ambition that are really tied up into the actual workings of science. Another thing that is tied up into the workings of science is money. You need money to do science, whether it's fairly inexpensive science like I do, where you need some travel money and some graduate student support, or very, very big science where you might need literally billions of dollars to do something like discover the Higgs boson or detect gravitational waves. So my guest today is David Kaiser, who's a professor at MIT and a really unique thinker in this field because he is both a practicing physicist, he's a theoretical cosmologist like myself. He works with Alan Guth and other people at MIT on what happened in the early universe, black holes and inflation and stuff like that. But he's also a working historian of science, and he studies especially physics in the 20th century, which was, let's face it, a go-go time for physics. Not only were there great intellectual revolutions going on, but once the Manhattan Project had come, physics was the glamour science. Governments could not give enough money to physicists. That situation, if you've been following along, has been changing. It's becoming harder and harder to get money for physics in particular, but arguably even for science in general. So David, one of the things that he's been thinking about these days with a new book coming out is how money and politics and science, physics in particular, have all intersected over the course of the 20th century. It's a fascinating story because the physics is interesting. You know, what are you going to do when you have money? What are you going to do when you don't have as much money? But also, of course, the human side is interesting. How do you make these decisions? There's essentially an infinite number of interesting things you could do, given world enough and time, given money enough and resources, but you have to make choices about what to do. So there's just no choice that we need to take seriously the intersection of money, politics, and science. This is the podcast to go to if you want to know how that played out in the 20th century and what the implications for that are going forward. I also want to mention I hope everyone is doing well, staying safe, and keeping busy during the pandemic, the coronavirus COVID-19 issue that we're all facing worldwide. As I mentioned, I think before on the podcast, one of the things I'm doing is starting a little series of YouTube videos, very informal, me in front of a camera kind of stuff, where I talk about some of the great ideas in physics and in science more broadly. It is called The Biggest Ideas in the Universe. You can check it out. The idea is that every week I'm going to put out a video, and then people will ask questions in the YouTube comment sections or on the blog where I blog post it, and then I will pick out some of the best questions and answer them in a video a couple of days later. So this is not in any sense supposed to be a way to learn about the virus or pandemics or anything like that. It's a way to learn about the universe, and I think that it's still important to try to learn about the universe even when we're trying to live in a world that has been so dramatically changed by this kind of event. It's important, as I say elsewhere, to both keep living, but also to grow and move forward. This is my way of helping us all do that. I hope everyone is doing it the best way they can. So with that, let's go. David Kaiser, welcome to the Mindscape podcast.
Thanks so much for having me.
Good to have you on. You have this wonderfully interdisciplinary world, life, role, whatever it is, at MIT, working physicist, writer, and historian. Am I missing anything? Policy person?
Well, not quite policy, but I did just take on another role, which is a bit nutty. I'm now an associate dean for social and ethical responsibilities of computing. So,
of computing?
Of computing. We have a brand new College of Computing, and so that's where I mostly wear my historian of science cap. Say, how can we think about science and engineering in broader context? And so that's what I try to bring to that new role as well.
All right. So, do you code?
Very little. I mean, I have friends who code, which
Back
is like
in
the
day,
best
maybe,
thing.
Were you?
Modestly.
Yeah,
nothing
that
like
was
the
me.
fancy stuff today. Modestly.
No, that was me. Basic, quick basic.
Yep.
On IBM PCs was
Yep.
my
And
peak.
I love Mathematica. I will shout out right in Maple. That's my level. Anything beyond that, I need friends and students fast.
So just right to the ethical considerations for it.
Exactly.
I like
right.
that.
Yeah.
So we're here. I think I wanted to concentrate the chat on science and money, which just saying the words out loud, it's a slightly ill fit, right? Strange bedfellows, but necessary ones. They're definitely bedfellows.
Yeah.
Maybe history is the best place to start. Like, even when we were inventing science back in the day, Bacon and Galileo and whatever, how did they get paid, those scientists? Did they apply for grants? How did it work?
They didn't apply for grants in a direct way. Some of them were paid by a kind of local government. And so Galileo's first paying gigs were working for the Venetian Senate, or among his first. And he was very crafty, and he could arrange these great kind of demonstrations to get their attention, like the telescope that he did not invent, but certainly improved. He basically sold it to them as a military defensive device. You could see the oncoming ships quicker. And they said, this is great. We're giving 100 scudi per year back when, or 1,000 scudi, and that was when 1,000 scudi really meant something. But he was he was a crafty, smart guy. And so before long, in fact, within about a year or less, Galileo had parlayed this to a different sort of supporter, and he moved very rapidly to be the kind of court philosopher for the de Medicis.
Okay.
And so he moved to Florence, and he was set up as a kind of in-house researcher, but his main job was really to make the de Medicis look good. It was one more kind of bauble for court. His job was to be kind of terrifically entertaining at dinner, like all the physicists and astronomers we know today. He fit perfectly that mold. So he was really very expert, and it turns out he was by no means alone. So Kepler was, imperial mathematician for a different emperor, I guess, Rudolf II.
And sorry, I don't want to gloss over too quickly the idea that Galileo's first monetary source was defense funding.
That's right.
In a sense, that goes back to Archimedes, right? He had the same thing.
That's right. No, I don't want to suggest that Galileo invented it either. That's right. These are really long-standing trends, and what we see with Galileo and really his generation is this kind of a variety of possibilities. There is literally a sort of a city-state government, something like a local government.
Nations were not the big thing at the time.
Not in Italy in particular. Around a little bit later in that century, a couple decades later, nation-states did start making formal institutions to support research, like the founding of the Royal Society in the 1660s in England, and the French Royal Academies founded around the same time. So there are some kind of academies, not quite universities. They're really meant to be almost more like we might call them think tanks today, supported by the crown or by
research
some central
institutes.
Government. Exactly, that's right. And more often than not, throughout much of Europe, it was a kind of local duchy or a local noble person in the family.
Tycho Brahe, an example of kissing up to the local nobility.
Yeah, got him a whole island, right?
Yeah, got an island with the various observatories
and
built.
Lots of serfs to do a lot of work. It was really
and he collected a lot of data. It was the big data era of astronomy was launched back then.
Exactly. With basically private funding from a kind of local royal.
So for Galileo, was the switch from sort of government money to local nobility money intentional in the sense that he said, look, I would rather be supported in this way?
Yes, it was very much intentional. He really was very crafty. So it was not only that he would get more money, which he did, he would lose his teaching obligations, right? The guy was no dope. So he was teaching at the local university and being supported by the Venetian Senate, in Venice or Padua. And then when he moves to Florence, his job is to think grand thoughts all day and be very interesting at dinner.
Right? I recently visited the Galileo Museum, which, by the way, is not a museum about Galileo. It's the Medicis Museum, and it's like all their baubles, and he was the greatest bauble.
He was a great bauble.
Still today, he's the draw.
That's right, yeah. And like I say, he was maybe among the most kind of clever or conniving of that cohort, but that was really kind of the default approach for much of what we would now call the scientific revolution.
Right. But how formal was it? I mean, how many scientists were there asking for money?
That's a good question. It's hard to know. This was just the time when the first things we might recognize as learned journals were being founded. So we can go back to libraries, to particularly well-stocked libraries today, and go page through kind of rare books or rare journals. But even there, the notion of a professional scientist was not quite what we'd recognize today. That's really a notion that emerges over the 19th century.
We should say, what years are Galileo?
Right. So Galileo's big breakthrough is 1609, 1610. His his famous trial with the Catholic Church is 1632-33. So that period.
Mm-hmm.
So right contemporary with Johannes Kepler, therefore a little bit later than Brahe, but all in that same time period.
Right. And I guess it's also sort of about the same time when universities were taking off. Is that fair? They were there already,
Some
but
were
they
there.
Getting bigger.
They were getting bigger. They were also not usually the sites for research. They were very involved in teaching, often in many parts of Europe teaching clergy, and so they had a different role to play. The oldest universities in Europe date back to the 12th century, to 1100. So even half a millennium before Galileo. So they were around there for a long time, but they were not sort of seen to be where it was at. I mean, Galileo was eager to get out of a university position and become court philosopher. So they were there. They were indeed growing, but they're not the main story for a lot of science in that period.
Is there any thought that either Galileo or his many friends and enemies worried about this situation, either the defense funding or the private funding? Like, were they already thinking about ethical considerations, or like, thank you, there's money?
Yeah, I think a lot of it was thank you, there's money. And that person over there has even more money. Thank you very much. So that's my sense of it. There were wonderful sounding charters. When we get to the kind of nation-based societies like the Royal Society or the French Royal Academy of Sciences in Paris, there are these lovely kind of ornate charters, very aspirational. It is to for the betterment of humankind kind of language. But if you go and look at what they were mostly supporting, it's I'm not sure we see. We see a hodgepodge, and I'm not sure that it was affecting daily practice so much. It was a nice thing to say. So
I certainly think of poor Descartes, who made his money being a tutor for various princesses and ended up dying of pneumonia because he had to move to Sweden. Was it Sweden?
I can't remember where. He certainly had to leave France. He was in the Low Countries, in Holland for quite a while. I'm not sure where he wound up dying, but he had to get the heck out of where he had been. That's for sure. Yeah.
But by the time of Newton, which is soon after Galileo, I mean, I think of him being at Cambridge University.
He was. That's right. So both as a student and then where although, I mean, as you probably remember, Sean, he got most of his kind of most world-changing work done away from campus when the campus was closed because of the plague.
It's true.
So I always tell my own MIT students, you'll do much better on spring break or, over the summer. Don't listen to me.
As long as you're Isaac Newton.
As long as we're not fighting the plague and as long as you're Isaac Newton. Two ingredients. But you're right. So then Newton did make much of his career as a professor at Cambridge, teaching mathematics or kind of applied mathematics. Although even later in his own life, again, as you know, he left that and became a master of the mint. He was overseeing England's printing of money, coins mostly, and he delighted in prosecuting alleged counterfeiters and cutting off fingers, and he had a nasty streak.
He's a terrible person.
He had a nasty streak.
But also not doing that much research by that time, or at least not doing physics research. He was definitely doing biblical research.
He was doing a lot of biblical research throughout, and also alchemical research, even experimental things. And that was continuing through much of that period, although he did work on his optics. His sort of second major famous work of science, I think, is from that later period in his career.
Okay.
Might have overlapped a bit more.
And, being a physicist rather than a historian, my history tends to skip over the entire 18th century.
Right.
But one thinks of Benjamin Franklin, people like that, again, not university affiliated.
No, that's right. And to my mind, for our beloved field, Sean, a lot of the work that we would look back to was being done in the 18th century, the 1700s, a lot of it in France. And a lot of those folks were kind of associated or supported by the Royal Academy. Some of them were based at universities, but a lot of them had basically stipends to do interesting work. And every now and then they would compete for large prize essay contests. And that's where a lot of the work that we would just take for granted today by Lagrange, by Laplace, by Poisson, by names that we know from our physics textbooks. That's really the cohort who kind of nurtured and expanded the Newtonian framework, just so much beyond what Newton himself had ever lived to see.
I love the idea of essay contests as a way to make a living. And it continued on, right? Poincaré very famously, discovered chaos theory, roughly speaking, by his essay.
That's right. Look, even some of Stephen Hawking's most important work was submitted first as essays to the Gravity Research Foundation. Essays, a contest that continues to this day.
I've done that. I think I won second place in that one year. Yeah,
you're in good company. Hawking did not always win.
No.
He often got honorable mentions.
Yeah.
So.
It has to be a pretty sad essay not to get honorable mention in that contest. And I think that there are some pretty sad essays that enter it.
Right.
But okay, so is this taxpayer dollars in some sense that are funding the academies?
So to speak. They're certainly coming from the royal budgets, which themselves are coming from all kinds of collections, taxes and tariffs on the people. So in that sense, they are state-funded, kind of by the crown when there still were crowns. But it was coming from the kind of, let's say, the central bank account. It was in that sense, it was being funded predominantly not by local industries, certainly not by student fees, by tuition.
Yeah.
It really was predominantly kind of national level government expenditure by that point.
And I guess I should ask, did these people think of themselves as scientists, as physicists? Like some people thought of themselves as mathematicians, even though you would now call them physicists?
That's right. So the catch-all term most of them would have recognized would be natural philosopher, which I love the sound of that.
Still true. Yeah.
Still true.
Still great.
And so it's, again, good to remember that although the word science was in the English language for a long, long time, the word scientist was invented. It was actually introduced into the language in the 1830s.
Yeah, it's amazing.
Well after this period, even of the Laplaces and Lagranges, let alone Newton or Galileo. So there were words like astronomer. There were words like you said natural philosopher and mathematician. And so one of the things that Galileo, in fact, wanted to do was shed the lower status title of mathematician. He was basically a mathematics professor, supported in part by the Venetian Senate. But he became a philosopher. That was so much more special to him and to his generation.
Those were the days.
Those were the days when he moved from low-level mathematics, lowly mathematics, to being an actual court philosopher.
Wow. And then, okay, so I really do want to get to the 20th and 21st centuries, so we're skipping quickly, but 1800s, I'm thinking of people like Maxwell and Boltzmann, and again, some mixture of universities and big research centers, the Prussian Academy.
That's right. And so the 19th century is really a sort of time of really vast transformation in the role of what we would eventually call scientists. The word itself starts being used in English. The institutional setting, the role that people are kind of hired in to do. It's no longer a kind of gentlemanly pursuit. Now there really is a profession. You can go to school, get trained, and get a job as something called a scientist.
You can tell your parents you want to grow up to be a scientist.
And be the wrong kind of doctor, but not a medical doctor. That's right. So that really is a story of the kind of transformation over the 19th century. So people like Maxwell were based at a university for much. He was at Cambridge for much of his career. And he starts, in fact, innovating even within there institutionally. He becomes the founding director of the new Cavendish Laboratory. So it's amazing that he was this mathematical physicist who handed us, so much of the kind of basic theoretical physics we use day in and day out. And his big promotion was to become an experimental physicist.
The head of a lab.
Yeah, that's right.
And of course, the Cavendish is still one of the world's best labs.
That's right.
Sense.
And that was part of a move by, again, a kind of national government as well as the local university. But it was part of a move toward a kind of intentional investment in science and engineering research for kind of national betterment, often tied in that period to kind of imperial ambitions. Mm-hmm. We'll have better telegraphs, we'll have better, ships at sea, we'll conquer navigation. So some kind of applied projects in science and technology for kind of nation-state betterment or defense, but not always limited narrowly to that. And so there was room for, investigations that were not tied narrowly to a project. But the point is that national governments now, not just individual monarchs or kind of, aristocrats, but actually kind of national governments with a more articulated set of institutions, they began supporting what we now would recognize as scientific research.
Was it always true, even back to Galileo, that to the extent that there were nation states or at least local city-states, people appreciated that science was helpful, even whether or not you call it science, natural philosophy was helpful to national greatness, or was that a latecomer on the scene?
Oh, it was certainly a useful talking point, but what was a measure of national greatness, one of the best things that Kepler kept doing to keep his job was casting really good horoscopes, right? So he was a terrific astronomer, and what the court wanted, among other things, was advice on, national affairs. We better consult the stars. Who's our astronomer? So,
right, okay.
So they were considered useful, but not always in ways that we might expect.
No one is a bigger believer than I am in the importance of always keeping learning, being exposed to new ideas, making your mind expand. And the Great Courses Plus is a great service that helps you do this. It's a streaming service that brings to you college-level lectures from some of the best professors, thinkers, and lecturers out there in the world, from the top universities, from National Geographic, Smithsonian, and so forth. It's college-level learning without student loans, homework, grades, and all that stuff. And the Great Courses Plus app makes it possible to learn whichever way works best for you. You can watch or listen to lectures at any time. So one course that I really like is called Black Holes, Tides, and Curved Spacetime, Understanding Gravity by Benjamin Schumacher. It's a thorough introduction to the mysteries of gravity, from Newtonian gravity to curved spacetime to gravitational waves and so much more. Right now, Mindscape listeners get a wonderful offer of a free trial and only $10 a month once you sign up for a quarterly plan. So you can get the details at thegreatcoursesplus.com/Mindscape. That's THE greatcoursesplus.com/Mindscape. Okay, and so we move up to the 20th century. Is that okay?
Yep.
Let's take a little bit of a detour because I want to talk about Einstein a little bit.
Sure.
Obviously he was pretty good. He wasn't in the popular press labeled a physicist. I think that he was often called a mathematician.
That's right. Yeah, there was a continuing kind of both labels would be used for a long time.
But also he famously bounced around jobs,
Sure
right?
Did.
And
yeah.
do we want to talk about the extent to which that was because his ideas were so radical that people couldn't take him, or just sometimes it's tough to find a job and everyone knew he was brilliant?
I think it's closer to the latter, but even there we have to append an asterisk that not everyone knew he was brilliant in those early years. In fact, he'd made an awful lot of powerful enemies, or at least people who were pretty annoyed by him.
He rubbed people the wrong way.
He rubbed people the wrong way. He was awfully arrogant as a young man, as was Galileo, in fact. In that, they share many things.
Yeah.
And he was quick to let professors know that not only he thought their courses were boring, so he just wouldn't ever show up, they were hopelessly out of date and doing unimportant things.
Yeah.
And it's one thing to think that, as I'm sure many of my own students probably still do about me, but thankfully they don't tell me that to my face. Einstein had no such problem just saying, hey, Professor Weber, this is just a waste of time. See ya.
And he might have been right.
And he might not have been wrong every time, but although, of course, as you know, sometimes it came back to bite him. So he cut his math classes, and then 10 to 12 to 15 years later comes crawling back to his friends who had taken the classes, whose notes he had borrowed, and said, oh, gosh, it turns out geometry is really important to me now.
Free money and stuff. I need to know it.
That's right. So even there, sometimes came back to bite him.
But again, mostly his career was spent at universities one way or the other.
Not right away, but he gets actually, I'm not sure that's true. His first job paying gig out of his university studies is as a patent clerk. He was hired as a patent clerk, third class. As I always say, there was no fourth class. This was an entry-level job. He got it not based on any merits because the father of one of his close buddies pulled some strings. It was, even for Einstein, it wasn't what you know, it's who you know. It's very sobering. He dives into the work, as far as we can tell. He seemed, he'd been fascinated by kind of electric gadgets as a kid. This is the age of electrification. He famously recalls when an uncle gives him a compass when he's really young. This is just mind-boggling. So both his father and his uncle were early kind of electrical engineers who kept failing at business, so they seemed to be pretty good as engineers. So Einstein, I don't think he necessarily saw this as a bad place to start. I think he loved kind of these gadgets. He worked closely with experimentalists for many parts of his career and tinkered with apparatus. So he starts there.
And Peter Gallison makes the point pretty persuasively that his work with clocks later became important.
Exactly. With the real machinery of coordinating clocks across a distance. That's right, exactly. I love that book that Peter wrote. So he's immersed in this kind of electrotechnical kind of modern era as a patent inspector. He publishes he submits these 4 articles in only the space of 6 months of 1905. We call 1905 his miracle year. It was his miracle season. The guy took half a year. Really,
by the way, likewise
months.
Newton, right? Didn't he invent all of classical mechanics over that break when they had the plague?
He was awfully quick. That's right. But unlike Einstein, Newton sat on it for decades. So that had to be pulled from him from these sort of unpublished notes. Einstein was publishing these things, so we can date them and so on. We know when they were received at the journal, by and large. But So these things come out in 1905, and the response from his employer is not even to promote him. He doesn't even get promoted to patent clerk, second class. No one's reading most of these articles for years. So his first academic gig is basically about 4 years later. It's an entry-level position at a kind of out-of-the-way university. A few years later, he's poached somewhere else at a marginally less out-of-the-way university. He moves around 3 or 4 times in the space of 5 years. And then in spring of 1914.
Both because he he was gaining more renown, and also he was a climber. He wanted to be at these bigger places.
That's exactly right. No, that's a great point, Sean. We have housed indeed at Caltech this amazing international effort to publish and edit Einstein's collected papers, his correspondence, both incoming and outgoing. It's an amazing team led by just a terrific historian, Diana Buchwald-Kormos. And so we can watch, thanks to that group's help, this day by day kind of grappling with hard ideas, dealing with a marriage that's souring very tragically, and then also indeed a kind of social academic climber, to be sure. So we have that going on over the course of not quite a decade. He's sort of in the patent office, really unknown, and 9 years later he gets the call. The call is not to do more teaching. The call is not to a university post. It's instead to become a member of the Prussian Academy of Sciences, where he doesn't have to teach, and he gets resources to conduct research, and his job is to think. And when he leaves that, when he basically refuses to return to Germany after Hitler takes power some years later in 1933, Einstein hops ship to the Institute for Advanced Study in Princeton, which is also not a university, where again he does no teaching.
Technically, it's not a university. That's true. It's very closely
no formal
connected
classes.
To,
it's affiliated with Princeton University.
That's right.
But he was not, grading students' papers late into the night. He wasn't formally
Caltech
teaching.
tried very hard to get him. I don't know how much of
right.
that story you know, but
yeah.
he loved Los Angeles and Hollywood. He loved hobnobbing with the stars. And what I'm told, I'm not sure how much on the record or verifiable this is, that the final straw was just that Caltech's president was so anti-Semitic that Einstein couldn't put up with it. And he complained about anti-Semitism at Princeton, but Caltech was just too much.
Yeah, and unfortunately, again, as we now know, Caltech was more in the mainstream of American universities, elite universities, than the exception at that point. So a similar example from right around that time, from the late 1920s, when J. Robert Oppenheimer was first hitting the academic market very young. He skipped grades in high school, graduated Harvard in 3 years. He was taking Ph.D. level courses in physics his first year as an undergraduate. He's one of those people. Zooms off to Europe for his Ph.D. and is immediately and a quick postdoc. And is snatched up by both Berkeley and Caltech for tenure track, or effectively almost tenured positions. And the Berkeley department chair had to fight to get him appointed because they already had one Jew on the faculty. In circa 1929. That's right. And so they make an exception for this, indeed exceptional person. But the point is that the anti-Semitism in hiring and indeed in student admissions was pretty rampant across the United States, hardly unique to Caltech then. But it did indeed affect some of Einstein's own, opportunities.
So at what point in this process does the idea of applying for grants appear? Is that something that is coming on the scene at this time?
Not in the way we'd recognize it. No, a lot of this research was being...
maybe we should explain to the audience, who are not all professional physicists, what it means to apply for grants.
Not everyone knows about that. Is that not how we all spend our time? So it really, in recent years, and indeed in recent decades, the way the vast majority of scientific research is supported in the United States, but now really commonly in many, many parts of the world, is that researchers will submit a grant proposal. I will propose to do the following investigations. Here's why I think they're important. Here's what I expect to be able to find. I'll need this much time and this much money over that time. And you submit that to a variety of kinds of recipients, either a federal agency in the United States, the National Science Foundation, Department of Energy, NASA, National Institutes of Health, and so on, or increasingly, as maybe we can come back to in this conversation, increasingly to private foundations, or on some occasions to individual private donors. Usually it's, or indeed to a private industry, a corporation, or a kind of industrial laboratory. So you say, if you can give me this money, I can do this work on this project. Not so to speak for you, but I pledge to do this project as best I can over these years.
Maybe national greatness will be enhanced.
and then I'll come back with hat in hand, really soon. And so that's a contract basis, meaning university. So for university-based researchers, right, like you and me, our home universities will, on our behalf, in the formal contractual sense, we submit a proposal to our local university. Their main office checks it over. Okay, it looks right. Then they will submit it, for example, to the National Science Foundation. There'll be a whole panel of peer review, and priorities will be hashed out. congratulations, MIT, we will now fund this proposal from researcher, X1329, whatever my code might be. That's not my code. But anyway, so from your local researcher, and then the money will be transferred to the university, and then eventually, I could spend it to hire a student or some modest equipment. So it's built on the model of kind of co-equal business partners. It's not a charity. It's not cast as a charity. It's not a gift,
right?
Which is different from before, from longer ago in history. It is. We have two autonomous agents,
and it's very formalized,
very legalistic, extremely formalized. That's exactly right, and not just in the accounting, but in the language. What's allowed by this agreement? It's a legal contract, and with all the headaches that might imply.
Just to illustrate, you can travel to a conference and pay for your hotel using grant money, but there is a limit on how many dollars per night you can spend.
That's
doing
right,
that.
And don't charge alcohol to it, which is perfectly appropriate not to, but things like that. There are limits on what it can be spent on and how much per category, and that has to be really spelled out. And often, if you want to change the allotments, I need to make another trip to Vienna to meet with my colleagues, but I only budgeted this much for international travel, and it's a negotiation. So that's the current process, and it really was put in place not in Galileo's day, not even in Einstein's day. That emerges from the Second World War. Okay. It's pretty recent in history, and it was literally engineered by an MIT researcher and kind of administrator named Vannevar Bush. He had been dean of engineering here. He helped found Raytheon Corporation in the 1930s. He was basically an electrical engineer. And his real brilliance was really in administration. So he was tapped by Franklin Roosevelt even before the United States formally entered the Second World War. Bush became kind of the person in charge on how to organize science and engineering for defense, for the nation's sort of clearly soon-to-be defense effort, even before the surprise attack on Pearl Harbor. Right,
we were in the war. Yeah,
there was a kind of preparation going on, and Bush was really one of the chief architects of that.
Related to our President's Bush?
I think there was no relation, same spelling, but no, I don't think there's any direct connections that I know of. And so Bush is interesting, like many of the kind of elite university administrators of that time at a lot of, especially private universities. Many of them were very strongly anti-New Deal. They didn't think the federal government should be moving into education. That smelled of like central planning. So they thought that the federal government had no business in the job of education. They shouldn't be involved in universities. So there were failed efforts before the Second World War, for example, here at MIT and other places, to actually get federal support for research on campus, and those would just sort of fizzle out. That was not the template. That was not the model. That changes very rapidly in the early 1940s. And so Bush didn't want to have even the appearance of a kind of, what smelled to him too much of a kind of socialism. Fairly or unfairly, that's what he thought this would lead to. So he said, we'll have a business contract. Right? We'll have a private sector model, free market kind of model. Two autonomous agents will enter into a binding legal agreement. The federal government needs us. We need them. Two parties come to the table. We hash out a deal, a contract. And that becomes the kind of the basis for grant making that ramps up at an unbelievable rate during the Second World War and really never slows down or doesn't slow down for a long, long time, for decades afterwards here in the U.S., and that quickly becomes kind of exported as a model to support research many places beyond the United States.
World War II clearly changed everything about science and money, and I think that if you told the person on the street that was true, they would agree with you, but they would attribute it all to the Manhattan Project and atomic bombs. But it goes far further than that, right?
It really does. And this is a fascinating period of history, and I've written about it, and I'm continually kind of just amazed by it. So both the radar projects, the Allied efforts in radar very quickly were shifted to be headquartered here at MIT, and the Manhattan Project, which was much more sprawling, that wound up having more than 30 locations across both the United States and Canada, with large inputs from the British and Canadian contingents. So it wasn't just Los Alamos, it was 36 sites, contracting sites, some very large. Those were incredibly important examples of this new relationship between the federal government, in particular the military, the kind of War Department, as it was then called, and often university-based researchers, physicists, chemists, engineers of many, many stripes, metallurgists, linguists, social scientists as well in some of these projects. But that's you're right. That's not even the biggest story by some ways to measure it. There was an even more fervent effort, starting even before the Manhattan Project was kind of scaling up, for a different kind of partnership with research, with science, and that was to train lots of people in rudimentary physics.
Yeah.
And I found this really fascinating. After World War II, the phrase "the physicist's war" was used all the time, and people would use it to refer to radar, but especially the nuclear weapons project, to Los Alamos and the bombs. And that's how the term gets kind of reinterpreted. People would say in a very quick reminder, World War I was the chemist's war, think about poison gases and so on. World War II was the physicist's war because of these kinds of projects, and they mean almost always radar and the bomb. It turns out the usage of the phrase physicist's war, as we can now tell by tools like Google Ngrams, we can search huge corpora of English language text, that the usage of the word spikes while the Manhattan Project is barely existing and still classified, while radar is slightly bigger and still classified.
So the people on the street don't know that these things are going on.
Right. These newspaper editors are not spilling secrets. They don't even know about them.
Yeah.
They use the term to refer, as it was used routinely in congressional testimony, and it was in the public face a lot in the early years of World War II. But it meant this massive training program to train often kind of enlisted soldiers, service members, across the various branches of the military in really rudimentary physics. The modern battlefield meant you had to know something about electronics and circuits and radio for really kind of rudimentary communication, something like sound ranging. How do sound waves propagate through a battlefield so I know that the sniper shot was from here, not there? So how do you measure, humidity and angles and basic atmospheric conditions? Yeah. So it was what we would consider kind of really high school level physical sciences. It was certainly not esoteric nuclear physics that was being really rapidly sought. And this remade many, many American campuses. There was a huge push to get enlisted members onto campus for short, very, very intense, 7-day a week, many hours per day instruction in basic physics. This was called the physicist's war. The first academic specialty that started getting draft deferments were physicists, not so they'd make weapons, so they'd stay in the classroom. People who were in everything from mathematics to music to philosophy, faculty, were kind of drafted, not drafted in a formal military sense, were grabbed on so they could also teach rudimentary physics to these enormous auditoriumfuls of enlisted service members. So that became the physicist's war. It's that the modern battlefield needs what we now call classical physics, and we need hundreds of thousands of people to be cognizant of these things. So it remakes physics, it remakes large parts of the university, and it really solidifies this increasingly close working relationship between the federal government, including the War Department, the military and defense branches, and academic research.
Do you know the story of the Caltech football team?
You can tell me it. I'm not sure I do.
Caltech is not, a sports powerhouse in the NCAA in any stretch, but if you go to the gym, there's a little plaque that mentions that the 43 Caltech football team is in the Collegiate Sports Hall of Fame. And there's an explanation if you go online. The explanation is the following. There was no football at Caltech, right. But during the war, basically a whole bunch of Army soldiers who had been training at Stanford or something like that were moved to Caltech to train at Caltech. Yep. They wanted to play football. Caltech didn't have a team.
Right.
So they hurriedly put together a schedule which consisted of 2 games against the University of Redlands and 1 game each against USC and UCLA JV teams.
Right.
And so these soldiers destroyed their competitors by in 4 games, the total score was 230-0. And such a show of bad sportsmanship got them into the NCAA Hall of Fame for being one of the best football teams of all time.
Well, congratulations.
Yeah,
you and your students will be very proud. I did not know that story. That's fantastic. But it all adds up. It's a great example of these campuses were really overrun. At MIT, by a few years into this sort of project, there were sort of 3 basically enlisted service members on campus for every 2 ordinary students. There were more people in these special Army and Navy courses across campus than kind of ordinary college students. That's also why a lot of campuses switched to a trimester or a quarter system. You got to squeeze more stuff in shorter amount of time. There's a war on, buddy, that kind of mentality. So it really has just an amazing impact on campuses and on the structure of American higher education.
Did it change the appearance of physics in the curriculum for non-military students?
Oh yeah, I mean it was. The emphasis was basically get through this, again, kind of, we might think of kind of high school level stuff, because half the high schools in the United States weren't offering any physics at all.
Yeah.
People, sort of astonished officials began to realize. So a lot of it was pretty rudimentary. There were expert panels advising groups like both the War Department and the Office of Education, the Federal Office of Education during the war, panels of university-based physicists. Part of the American Institute of Physics would help staff these kind of blue ribbon committees. And they explicitly argued that departments should not offer useless material like nuclear physics during the war, again, in hindsight, because that will take too many resources, too many classroom hours away from what the campus needed to fulfill. There were all these formulas that anyone who was seen as poaching legitimate physics instructors. I mean, if you're getting a music professor to go teach, Newton's mechanics, they really want to get all hands on deck. So to the extent that universities might be jockeying to hire, some hotshot from another campus, there would be, you'd come in for very strict, get a very strict talking to if you were disrupting this emergency physics instruction.
So if I graduated from a good university or college in the 1930s, is it likely that I would never have had any physics in either high school or university?
If you were not a
physical
physical sciences student, yes, that's right. So there were something, I can't remember the numbers exactly, but something like half the high schools or half the high school age children, students were getting zero physics instruction at all on the eve of the war. Yeah, that's right. And on the other hand, you had people like Oppenheimer coming up who had so much physics as a student that he could jump way ahead in Harvard. So clearly this was unevenly distributed as so many things remain in education.
Right. Yeah. So clearly an enormous amount of money flooded into physics during the war, but then it didn't go away.
That's right. That's right. And so after, the very dramatic revealing of the presence of these bombs, and they were revealed in a horribly destructive way by using them against the Japanese cities of Hiroshima and Nagasaki in early August 1945, that by that point, physics was on everyone's lips, tied now to these sort of amazing or unusual or unexpected weapons. And there's another real a kind of amazing irony of history that happens there. We now know, many historians have looked in detail at this, and scientists of many stripes, what kinds of expertise did it take to build these nuclear weapons during the Second World War? Certainly needed some physics. It needed a lot of chemistry, chemical engineering, metallurgy, electrical engineering, and the list is very long. Some of the most visible experts associated with the project were physicists, Robert Oppenheimer, Hans Bethe, head of the theory division at Los Alamos, and so on. But a lot of it was, incredibly complicated work by, DuPont chemical engineers, scaling up reactors and making sure they would produce plutonium because they kept not working first.
Not so much biology, but these days there would be a much larger biological component.
That's right. That was much less significantly represented in the middle of the Second World War. It would begin to change after the war. That's right. So, but however, there was an effort to control what could be said about nuclear weapons once they were used. So in real time during the war, General Leslie Groves, who was the Army general in charge of the entire Manhattan Project, he commissioned a physics colleague named Henry DeWolf Smythe, who was a nuclear physicist. He'd been department head at Princeton, a very elite, well-trained nuclear physicist. And he recruited Smythe not to work as a nuclear physicist on the bomb project, but to work as a real-time reporter, as a kind of real-time historian of the project. He was given the appropriate clearance, and his job was to visit many of these sites, Los Alamos, Oak Ridge, Hanford, and many of the even smaller sites throughout the war, to write a report on how the weapon was designed and built that could be cleared and safe to release ahead of time. so that they weren't accidentally revealing the so-called secrets of atomic bombs, the atomic secret. And yet they knew there'd be an enormous need for information.
So they'd tell a story, but not the whole story.
That's exactly right.
They figured out what they could tell.
That's right. And so it turns out that this is where the first nuclear-based classification codes are actually literally codified. It's what can Smythe include in his report. Even after years after the war, if it's in the Smythe report, you can publish it. If it's not, it is de facto born classified. Yeah. So what do they decide is safe enough to release? In fact, the regulations even say that at the time secret rules that govern this report, information can only be released in the report if it's already widely known to professional scientists and in the published literature, or if it has no significant bearing on the construction of atomic weapons. What meets that test? A lot of nuclear physics. Had very little to do with how these things were actually made. It was either so widely known that it was the cat was out of the bag, or it literally was just not the stuff that people thought was most needed to be kind of locked down, which really was, how do you get uranium hexafluoride, this horribly corrosive gas, not to eat through your metal gaskets in these filtration systems? How do you stop the huge reactors at Hanford from self-poisoning so you can actually get plutonium out instead of having the reactions kind of halt? How do you get subcritical chunks of these very strange materials to get imploded together very, very supersonic speeds, which was not at all obvious. They struggled with that during the war. All of these are only barely physics problems. And those things were said, we can't ever let that stuff out, right? So the irony is the Smythe report comes out and it looks like physicists built the bomb because the Smythe report's filled with ideas about kind of elementary quantum theory and nuclear physics. And I should say this is work that really first came to light by a terrific historian named Rebecca Press-Schwartz and others historians, including myself, others have followed that trail since then. So it's another one of these, like, we all think we know what's going on. Oh, the physicist war. Oh, bombs were made by physicists, nukes. And you say, actually, gosh, it gets pretty complicated pretty quickly.
A lot of engineering and things that they chose not to tell us about.
And how did we come to tell that story is itself part of the story.
But I guess it's a little bit of a diversion from our self-chosen theme. But since we all of us probably listening here have all of our lives known about nuclear weapons,
right.
It's kind of hard to imagine what it would have been like. Just not only we have a really big bomb, but we have a really big bomb because of something about the laws of physics,
yes.
right? There's this new insight. It wasn't just we took the bomb that we had and made it bigger. Mm-hmm. There was this way of doing things we hadn't thought of that must have been a little scary.
It was scary, but I think that's right. And yet in the earliest moments, if we judge by a lot of the popular media coverage, newspapers and magazines, it was often combined with a kind of gee whiz. It was wrapped around a kind of the scientists, by which they almost always at that point meant the physicists, have conquered the forces of nature. They've conquered the reactions that drive the sun. Of course, they weren't actually doing fusion weapons yet. That came a few years later. But that's the language they would use. They've captured cosmic forces, and now we can make them do our bidding. And that sounded not just like physics was relevant. It seemed like physics was the most important thing literally in the universe. Right. And that, again, has just an immediate kind of unintended effect throughout, especially U.S.-based higher education, the spillover effects we can trace in many other parts of the world as well. So that enrollments in physics departments grow twice at a rate that's twice as fast as sort of all fields combined. It just races ahead. More and more people want to go into physics than ever before. Classrooms are bulging now, not with service members who need rudimentary physics, but with very smart people who say, I'm going to work on the forces of nature, on these cosmic mysteries and exciting projects. Funding is now sort of accelerating at a rip-roaring pace for physics, even more than ironically, than for some of those other fields that really were so important for applied military projects. And so one of the things I've looked at for quite a while is the kind of growth rates for enrollments, for funding, for job opportunities, but also even when we step away from the countables, from our kind of Excel spreadsheets. And just think about the kind of cultural place of the physicists in the years right after the Second World War. One example I love, there was a private, by invitation only little meeting for roughly 20 or maybe 24 hand-selected physicists in 1947. roughly 2 years after the end of the war,
Okay.
on Shelter Island off the North Fork of Long Island. This was a meeting, Sean, probably close to your hearts, where people first began figuring out how to use quantum field theories and make calculations that wouldn't always lead to infinities.
Taming the infinities, renormalization.
Incredibly important. The first successful answers were reported at the next one in that series. But in 1947, people were learning about brand new experiments that just seemed so you had to pay attention to them.
So names like Hans Bethe and Richard Feynman and Julian Schwinger.
That's exactly right. And Willis Lamb and Isidore Rabi present some of these newest experimental findings that really kind of electrify the group. They're brought together largely by Robert Oppenheimer, who by this point has left his Berkeley position. He's moved now to be director of the Institute for Advanced Study. He's now Einstein's boss, as the press would love to say it. And he gets government money to convene this very elite group for a kind of retreat where they'll go think about, the mysteries of the quantum realm together and how to describe matter in this quantum mechanical way. The reason I bring this up is that they met at this sort of American Institute of Physics headquarters in Manhattan, which was at the time in Manhattan, to take a kind of rickety school bus off to Long Island. And midway along their journey, they pick up a police escort, because someone says, hey, there's a bunch of physicists in that van. Those are the ones who won the war for us. That's why, such and such didn't have to, the U.S. didn't have to mount a land invasion of Japan, and all these kinds of stories that were circulating. Those are physicists. Another booster, a kind of recent veteran along the way, stops the bus and insists on buying a steak dinner, right, for all those. That's what starts to happen. There's another physicist, kind of bemused or surprised physicist around that same time, who writes that every dinner party, it needs physicists. They're paraded around sort of the women's luncheon groups in Washington D.C. among the socialites. Even people who had no role in the wartime projects. The job description of physicists suddenly meant something very different than it ever had before. And as I always remind my students, my favorite example comes from Harper's Magazine in the late 40s, where an observer writes that no dinner party is a success without at least one physicist.
We can all agree on that.
I said, where
they finally discovered that fact.
Yeah, and look at us now. I
still not invited to the best dinner
Where's
parties.
my invitation?
Yes.
That's right. But that's the moment of that real cultural shift.
I mean, one of the interesting features of this is physicists did play a very big role in the combat operations in World War II and the technology behind them that gave them access afterward, for decades afterward, to a whole bunch of money.
Right.
But the money wasn't narrowly focused on military applications. Those people in the bus going to Shelter Island,
right,
normalizing quantum electrodynamics, there were zero applications for that.
Certainly none that they had in mind at the time. Absolutely right. And that's another thing that I found really curious when I dug in and was doing some more kind of investigating, wearing my historian's cap. So the overarching kind of policy that took form very rapidly in this kind of chaotic post-World War II period was that we need to keep funding basic research in the sciences, and by which they almost always meant physics more than any others. Rightly or incorrectly, fairly or unfairly, science often meant physics to these folks, really quick slippage. We need them not because they'll make better widgets or gadgets or military devices, but so they'll be on call. We want to make what they themselves would often call a standing army. We want to have the world's greatest pool of talent. We want to make sure that they are technically proficient. They have the best equipment in the universe to kind of hone their skills on, even if they're not using that equipment right here and now to make better, military applications. So that if the Cold War turns hot, if a new outright phase of fighting were to break out, they wouldn't spend all that time staffing up the next Manhattan Project. Not only would they be there, the U.S. government would know who they were, where they were. They'd already be paying them. They'd literally be on the payroll. Efforts to make a national registry of physicists kick in this point. Not sort of for surveillance purposes, but to say we need to know where our technical experts are if and when we need them. And that prevails for nearly a quarter century. That assumption leads to an enormous kind of rocketing forward amount of funding, and enrollments follow suit, and job opportunities grow even faster. It's amazing.
Well, you use the phrase Cold War, and that's the point, right? Yeah. World War II ended, but the fact that there was still the Cold War going on, and there was clearly this technological race made explicit in the space race, but a much broader one, that absolutely fed into the idea that we need to keep throwing money at physics.
Absolutely. And remember, even long before Sputnik or the space race, a lot of people were very concerned about the proliferation of nuclear weapons, as many people are even to this day. But at that point, the United States had a monopoly even that statement is not quite right. The Manhattan Project had been a 3-country partnership. The United States, Britain, and Canada, one would have thought, had a tripleopoly or whatever. Although very rapidly relations soured even there. Yeah. So it became really a U.S. project, and relations were strained. Nonetheless, no other nation state literally possessed these things after the war. And all the projections seem to suggest that the Soviet Union, which was rapidly emerging as the kind of presumptive rival or enemy as the Cold War really set in, many policymakers in the United States convinced themselves they're such a backward people. They're kind of failing even at agriculture. There's horrible disasters of collective farming. They're a kind of backward rural people, not able to do this sort of gleaming high-tech science and technology. And of course, that was really, proven to be untrue within basically 4 years. So by by late August 1949, the Soviets had detonated their own atomic weapon, with some kind of complicated role played by espionage, but a lot of it was, historians and scientists have gone back over these things once many documents became available after the fall of the Soviet Union. It's not that this was a kind of carbon copy of the American bomb. There was a lot of hard work, major expenditures, trial and error. Nonetheless, this group of highly trained experts in the Soviet Union produced what the United States was confident would only ever be in the United States. And then that triggers this arms race. Soon it was felt that each country needed not just more weapons of greater explosive power, and then, of course, to a whole different means of making nuclear reactions release lots of energy, meaning switching from fission bombs of the sort that had been used developed during the war to fusion bombs that really do harness reactions more like what go on inside the sun. Yeah. And that is just, a kind of drumbeat, kind of terrifying drumbeat of activity from the late 40s right through really much of the 1950s, even before Sputnik and space race and rockets.
And, scientists are always happy to take the money if it's going to be out there, but there must have been some awkward rubbing of shoulders just because the culture of academia and intellectual freedom of speech, free trade, free exchange of ideas is a little bit different than a more closed-minded, secretive military mindset.
Right, that's right. And it was a kind of culture clash from the earliest days of the Manhattan Project, of Los Alamos in particular. And this was, again, famously kind of fought out, duked out by Robert Oppenheimer, who was the physicist and was the scientific director of wartime Los Alamos, who had to work very closely with Leslie Groves, the Army general, who was really in charge of the whole project. Groves favored a policy of very strict compartmentalization. So one should only ever have access to the information that you genuinely need for your own part of this large project. You compartmentalize the knowledge, so no individual has access to too many things. That was seen to be dangerous. And that clearly meant there was therefore huge kind of restrictions on communication, even among fellow scientific experts on the same project, let alone in the larger community. Oppenheimer won a kind of early battle with Groves by getting Groves to agree that people with the right kind of seniority, the right kind of literally colored badge at wartime Los Alamos, could attend a colloquium together in-house, still kind of classified, open only to those, that rather modest group. So at least they could brainstorm and kind of problem shoot things together, and not only be separated into separate compartments. Even that was kind of a hard-fought battle. It won Oppenheimer tremendous, accolades from his fellow scientists on the Mesa, and Groves gave in a little bit. But that was really that did not become the model for the project, or indeed for much work that would go on in the years to come. So that one of the great concerns that starts unfolding at places like MIT and many, many universities after World War II is not only is so much of this research being funded by the military branches, defense-related branches of the federal government, sometimes students are writing theses based on classified information. So, who can even serve on a student's committee is suddenly not so straightforward. Could the university library, stock a copy of the thesis? That's a big question, right, for a university. And so there was a period of real, we could say transition, but it was a kind of live issue. It was fraught for one or two generations. And it really comes to a head in the later 1960s. So, 20 years later, people fight over it, never quite gets resolved until the escalation of fighting in the Vietnam War. And that leads to just a tremendous kind of rethink of the military role in U.S. higher education. After the 60s, you find many, many, many universities adopting, some of them for the first time, policies that say, we will accept Defense Department dollars, but under these conditions, students must be able to publish their work. A renegotiation of secrecy, information sharing, freedom of expression.
They still wanted the money.
Yes. Unfortunately, it was the same time when a lot of that money was beginning to dry up.
Well, that's also true. People are still surprised when I sometimes tell them that through my life as a working physicist, much of my grant money has been from the Department of Energy,
right?
Because they think, well, isn't that like oil and nuclear power? And I don't understand what you do for a living, but it's not that, right? And this is part of that historical development, right?
Yes.
There's the National Science Foundation, but that's actually not what funds most of high-energy physics, including string theory or cosmology.
Right. Yep. Let alone big instruments, like huge equipment, but even people like you and me who work mostly with pencils and some modest computer work, like we were saying before. Right, so the Department of Energy historically is the kind of third-wave successor to the Manhattan Project. Now, of course, it's changed. Doesn't have the same, kind of job description as it once did. But the order of events is basically the Manhattan Project is founded in the early 1940s, is established in the early 1940s, in secret at first. Soon after the end of the war, starting officially in 1946, there's the establishment of a civilian agency, a nominally civilian agency called the Atomic Energy Commission, or the AEC. That's meant to take over the wartime Manhattan Project. It was a big fight. Should it continue being a military project or a civilian one? And basically the kind of compromise was it would be a civilian one with very heavy input from the military. More than just kind of liaison. But so nominally the War Department's Manhattan Project becomes a civilian federal agency called the Atomic Energy Commission. Then basically in the early 1970s, that's briefly renamed ERDA. I think that was something like Energy Research and Development Agency. And then quickly it's renamed yet again the Department of Energy. So we really can trace an unbroken line between the wartime Manhattan Project and the DOE. Now, the role of the DOE, the Department of Energy, has continued to expand and morph. It's not just the wartime Manhattan Project by any stretch. But nonetheless, it inherits that legacy. And so that includes a lot of the work at national laboratories, some of it now explicitly for defense research, and a lot of it now for unclassified, open-ended kind of basic research.
But all good things come to an end.
Yes, that's right. That's right.
There was, not only individual grants were booming in this era, but it was a period of tremendous discovery in fundamental physics. New particles were popping up all the time, right? And so starting in 70s, 80s, 90s, both the Cold War winds down and the discoveries dry up. So what happened?
Well, a lot of things happened. So the Cold War, in hindsight, we know, didn't quite end in 1970, but it sure looked like it might. There was a moment of what came to be called détente, a kind of a ratcheting back, at least, of some of the kind of rhetoric and real it felt like a hair trigger kind of tension. And there was a moment of a kind of reset in U.S.-Soviet relations. As we know, that then ratchets back up into a more hostile or antagonistic framework even by the early mid-1980s. But there was a moment. There was a moment in the 70s there where different priorities started to take hold at a kind of national policymaking level. And that coincided with a real economic downturn. So that's a period of what is often called stagflation. So you have stagnant growth, kind of rising unemployment, together with rising inflation. So a dollar would buy you less and less over time. And economists didn't think those two things would go together.
Yeah, people thought you either had unemployment or inflation.
Right. So this was a new, or at least an unanticipated phenomenon, and it really settled in hard. It was a very, very dismal time economically. And what that meant was universities, and especially university-based physicists, were hit with a double whammy starting in the early 1970s. There's major cutbacks in defense spending, part of it because of policy shifts. The kind of Cold War priorities are now being reevaluated. And combined with huge cutbacks in federal funding for education, partly because the economy's just not doing well. Then there's the oil shocks. I mean, it's a tremendously disrupting time in the U.S. and many parts of the world economically.
70s were kind of a drag.
70s were. I mean, it was just not more of the same. I mean, people were flocking to universities before then, often flocking still to fields like physics. And then a lot of them got there and felt a bit like, the rug had been pulled out. In the decade after the launch of Sputnik, so between the late 50s and the late 60s, the number of departments that offered PhDs in physics had doubled in the United States. It really was still a growth phase. We need more. And then we have this enormous glut in the country, and the bottom falls out. So much so that by 1968, there are many more young PhDs in physics seeking jobs than there are jobs, available or at least advertised. And then by 1971, the bottom is just falled out. The American Institute of Physics kept statistics. They ran a kind of clearinghouse to match up young physicists applying for jobs and potential employers. And by their own records, by 1971, there were more than 1,000 young PhDs registered for interviews, who wanted interviews, and 53 jobs on offer. That wasn't 53 university jobs. That included jobs at government labs, industrial labs. They all kind of cratered together. Largely because more than any other field in the academy, physics had gotten sort of hooked on a single source of support in the quarter century after the Second World War. Mm-hmm. Things had worked with the AEC or its close partners in the federal government. And when federal funding, shook, when that pattern became disrupted, physics had nowhere to go but down. Chemists had a century of experience partnering with industries and so on. Their funding went down, their student enrollments went down, but nothing is kind of cataclysmic.
They were diversified.
Biologists some of them are just beginning what would become an accelerating trend of biotechnology. Again, a kind of, we might say, a diversified portfolio, and to speak a bit anachronistically. There were varieties of ways of supporting very expensive research in other fields, and physics had just kind of never moved out of that kind of single source model. So physics enrollments had grown faster than any other field after World War II. They crash more quickly, more dramatically than any other field in the early 70s. It's really just breathtakingly symmetrical.
But then, the economy picked up in the 1980s, and yet physics still began to feel the squeeze a little bit. I know that you and I were both around in our formative years for the Superconducting Super Collider kind of disaster. Yeah. Was that an omen, you think?
Oh, yeah. It was,
maybe tell people what the disaster was.
I will. So the Superconducting Super Collider was an enormous particle accelerator that was under construction. It was proposed, and actually the funding was approved by the U.S. Congress in the mid-1980s under the Reagan administration. It was going to be, the design specs were that it would be not only the largest of its kind, but it would have dwarfed even the best machines on Earth to this day. And this was being proposed, 30 years ago, more than 30 years ago. It was a terrifically ambitious project.
So the SSE would have been much higher energy than the Large Hadron Collider, which we're also proud of right
exactly
now, that
right.
discovered the Higgs.
If it ever met its design specs by like a factor of 3. It really would have been substantially more higher energies and also more intensity, more sort of interactions per fraction of a second. And this was seen as a great kind of, more than a lifeline, this was seen as the future of the field, exactly the time when you and I were young students. What happened was the project kept getting more and more expensive, exceeding even the earlier cost estimates. And much more important, the Cold War ended. The Soviet Union dissolved. The Berlin Wall comes down in 1989. The Soviet Union itself dissolves, quite surprisingly or unexpectedly for many observers in the United States. That dissolves in 1991. And suddenly the kind of self-evident reason to spend money on esoteric, unapplied fundamental physics, like is there a Higgs boson, or what are the fundamental forces of nature? The reason to do that no longer is supportable or is supported by a majority of members of Congress.
Which is weird because it was never the right reason to do it.
It's right. I was talking about this recently with some colleagues in Europe, and they were like, "Why in the world did the Cold War have anything to do with funding this?" And it's such a U.S. focus. It was for me. It's like, how would you not know? Oh, right. Yeah. So it really goes back to a tradition that stems right back to the immediate aftermath of the Second World War. Early in the 40s and 50s, the federal government would fund duplicate machines, the sort of SSEs of their day. They weren't as radically expensive, but they were big, expensive infrastructure projects to make these particle accelerators. Their own scientific advisory board would say, we only need one. You don't need two. And they'd say, oh, but we'll keep morale high. The word they used was morale of the nation's physicists and make sure we can train that many more graduate students.
Such
we'll
delicate
build two.
snowflakes they are,
right.
yeah.
Yes, exactly. That's right. So the federal government paid for more stuff than even the physicists sometimes asked for in the late 40s, early 50s. When the U.S. entered the Korean War in 1950, the response was, we'll make more graduate fellowships for students in physics. The Atomic Energy Commission made a calculation in 1951 while the U.S. is at war in the Korean conflict, saying if this is a near quotation from their memos from memory, but it's pretty close. They say if N nuclear physicists are willing and able to use a particle accelerator, and if a reasonable team is sort of 5 people per machine, we'll just build the appropriate number, like N over 5, until the war ends, right? Not until they learn more about deuterons, right? Until the war. This was seen as not making weapons. It was seen as aiding this training mission. Well, that's the argument that no longer holds any water by the time the SSC's number comes up. Sean, we were both in Cambridge, Massachusetts around that time. I think we were. So when the final vote in Congress to kill the funding came up, it was October 1993. And I remember that because I entered grad school to study high energy physics in September of 1993. So I don't think it was personal slight on my behalf, but it really was.
It was planning, perhaps on your behalf.
If only I'd known then what I know now. And so it really was this dramatic dislocation. In fact, that one vote to cancel funding for this multi-billion-dollar project, the vote in 1993, meant that in 1 year, the federal budget for the entire field of high energy physics fell in half.
Yeah. No, I was just beginning my postdoc here at MIT that year, and we physicists in the Boston area had a town hall meeting where it was mostly therapeutic screaming, not a lot of good planning. Like, what are we going to do?
Yep. And it was again, with hindsight, it was a remarkable replay of what had already happened in our teacher's own memory, right? In the generation older than us, because this is remarkably similar to what happened in the early 70s. This enormous cratering, where the projections had been, we need more and more physicists. There'll be unlimited funding and unlimited jobs, and of course that's not sustainable. It crashed seemingly all of a sudden around 1970, 71. It crashed seemingly all of a sudden in the early 90s.
Europe did manage to build a Large Hadron Collider, and the United States sort of sheepishly bought in and gave some money as a junior partner in some sense. But these days, the United States has more or less, it's not even trying to build the next great particle accelerator. Europe and China are vying for the rights, and that's probably what it's going to be like for the foreseeable future. Right?
If anyone else can even do it, that's right. It certainly won't be in the United States. I think that much we can bet on with some certainty. Now it's really curious. At that, just a year before the SSC was canceled, the federal government, now a different branch, the National Science Foundation rather than the Department of Energy, but the NSF in 1992 began pretty substantial funding for what would become LIGO, a major infrastructure project that required major infrastructure.
The Gravitational Wave Observatory.
The Laser Interferometric Gravitational Wave Observatory, LIGO, which sort of paid off scientifically decades later. I mean, thrillingly, right? Thank goodness. But think about a quarter century of foresight to say we will invest civilian tax dollars at the roughly $1 billion level
in
over
something
the course
that,
of
by
decades.
the way, will never result in a gravity wave bomb.
It will not result in a gravity wave bomb.
Zero technological
Although I have to say, Sean,
applications.
Many of my very dear friends and colleagues have worked on that for most of their careers here at MIT.
Sorry, worked on
and
gravitational
Caltech.
waves, not gravitational wave bombs.
I'm sorry. I should thank you for correcting. I mean to say gravitational waves of the amazingly fascinating and non-destructive sort. Right? That's right. So gravity waves. And in the 80s, when people, before the funding came through in any sustained way, some people would say, they would add sentences, because almost out of habit, I assume, to their grant proposal saying, by the way, along the way, we might find, lessons of possible military relevance. Yeah. They didn't mean the gravitational waves will be weaponized. They meant we'll be learning more about electronics, computing, lasers. There could be spin-offs along the way, even if that was by no means the reason to do it. So it's a marker, again, of sort of how did one justify spending for even open-ended basic research. There was a kind of template in the U.S. that was frankly just never what took hold after the Second World War for all kinds of reasons. That's not the CERN model. It hasn't been. CERN was meant to be instead something to kind of heal the wounds
CERN,
of
the
Europe.
European nuclear physics,
that's right,
particle physics laboratory.
The center that's now based in Geneva, but multinational from the start. And it was from very early on bringing together representatives from countries that did not otherwise always, were not always close allies, and had to have a very bright red line demarcating anything that could possibly be construed as military relevance from this multinational basic science laboratory. So the CERN model was never hooked up in quite the same way to kind of Cold War politics or priorities. And the U.S. model had been remarkably effective with some waves. I mean, not in an unbroken way, but over the better part of half a century. And that number, came up right in our early years.
And part of this, the narrative around this is that the 20th century was the century of physics, and the 21st century is the century of biology. And biology is not only, visceral, and we all have it.
Yes,
not all of us think about physics, but we all think about biology every year a little bit more, right?
right.
But also, the individual biology projects are generally much cheaper than the individual big physics projects.
Right. Even the biggest big biology projects, some of which did get big, the Human Genome Project was hardly an inexpensive project. But when you look at just sort of, baseline appropriations, they were not the same. Is that one of the things that the physicists began to learn a little bit late, is kind of to their or our chagrin, is that by the time we got to the projects like the Superconducting Super Collider with an $8 billion price tag, then whereas maybe it would rise even to $15 billion, it wasn't so clear. That's now competing with, the kinds of budget items that make members of Congress really notice. It's not rounding error. It's not hidden in some boring document from some unimportant agency, right? That's, if you adjust for inflation, if you adjust for the buying power of a U.S. dollar, it's like 10 times more expensive than the Hoover Dam, right? It's now approaching the cost of things like designing and building the B-29, aircraft in the Second World War. It's at a level of major military projects, of major sort of civil society projects, of infrastructure projects, that then becomes a big target for people to look at more skeptically, maybe appropriately so. But that's what it's scaled up, and I think a lot of people in the physics profession didn't quite realize the shift of what it would mean to be arguing in what was no longer a blank check era for that kind of price tag projects.
Everyone in Congress loved the SSC until they decided where they were going to put it.
That's right. There was definitely it was not going to pay off in 50 states or many districts. But once site selection was completed, that's right. But even beyond that, the argument that we're locked in a existential battle with the Soviets. Well, there's no Soviet Union.
Right.
We need at all costs we need super smart trained physical scientists because why, right? And so the kinds of arguments that had worked really over and over again for generations, the arguments didn't make sense, and the price tag was so much larger than before that it just wasn't going to, it just crashed.
And something, just a science point worth making here is it's not just that we like building bigger and bigger accelerators.
Right.
There's certain kinds of science that can only be done that way.
Right.
So it's not a matter of if you pay half the money for the accelerator, you get half the science.
No, that's
If you pay half the money for the accelerator, you get nothing.
Right.
And so the question is, and it's a perfectly good question, is it worth doing this kind of science at all if that's the entry fee?
Yeah, it is a good question. It's a question that physicists need to grapple with, and of course many, many people beyond physics, no longer only up to us. And that was, again, made quite dramatically clear. So one thing that happens is there are these massive disruptions, like the cancellation of the SSC. They can have unintended intellectual consequences as well as sort of demographic ones. Who goes on? Who gets a grant? Who can get a job? Those are easier to relate to these big budget shifts. There are shifts in the kind of world of ideas as well, and that really fascinates me, both as a physicist and as a historian. And one of the things that begins to happen both in the crash of the 70s and again in the crash of the 90s, crash in funding and so on, is that some very, very, very smart particle physicists, high-energy physicists, begin kind of shifting their question base, asking questions in, for example, astrophysics in a way that simply wasn't common for them to do before the 1970s, not common in the United States, or to biophysics, or to other kind of hybrid areas, or condensed matter theory.
One of the very first Mindscape guests was Geoffrey West, who very famously, literally because the SSC was canceled, said, I'm not doing this anymore. Right. He had been a particle physicist.
Yep.
He became a complexity theorist and actually is way more influential and successful as a complexity theorist than he was as a particle theorist.
That's right. And again, sometimes they'll have these kind of happy endings with hindsight. Sort of didn't feel like an easy transition at the time, I'm sure. An example that I find really fascinating, it's close to my own heart and hopefully to yours, is the emergence of this field called particle cosmology, right? Which is an amazing, wonderful, exciting, super terrific field. I say that because I love it. I work in it, so it must be true. But that really was that was a kind of unintended byproduct, again, mostly in the United States at the time, of this kind of just huge reversal of fortunes in the physics field. Particle physics was hit harder than any other subfield in the early 70s. Again, funding was cut by 50% in a short window, much like what happened again in the 90s. And so you see this kind of intellectual migration. First thing that happens is many people leave grad school or can't get a job. That's one kind of effect. It's just grinding, double-digit unemployment rates for Ph.D. scientists in the 70s and again in the 90s. That's not that's not effective policy.
We had a physics colloquium at Harvard when I was a grad student there, how to get a job on Wall Street.
Yep. That's right. And so when I was in grad school, 2 years after the vote to kill the SSC, I think it's the case that every PhD in high energy physics went to Wall Street or kind of financial consulting. Every single one of them. That's another story. That leads to a different kind of bubble that bursts, as we now again know in hindsight. That leads to helps to fuel the dot-com bubble and collateralized debt obligations and all this fancy derivative stuff on Wall Street. But in the 70s, the first effect is an outwave of people just leaving the field. A secondary effect is that twice as many people leave particle physics as enter it in a narrow window. Even the ones who stay in science, who stay in physics in particular, they go to these kind of neighboring or hybrid areas. And it's not just by chance. There's a blue ribbon panel that's brought together by the National Academy of Sciences saying what happened in this crisis and how do we prepare for the next time. In this 2,500-page expert report on what happened to physics, I think it was actually called Physics in Crisis. Maybe it's Physics in Transition, but I think it was Crisis. The committee says the particle theorists, like you and me, particle theorists were hit hardest when the bad times came because we were most narrowly trained. They're saying this about the early 70s, that they had become so hyper-attuned to asking a certain kind of question, not being broadly trained in the committee's view at least. And that's why that group suffered even worse than any other field that also was undergoing real strain. So they say we have to change how we train high-energy theorists. Most of all, they have to be exposed to the broad areas of physics, different kinds of requirements on coursework and general exams. This is when you start seeing a new wave of attention, curricular, pedagogical, eventually in funding, to areas like gravitation and cosmology and astrophysics. So it's not so surprising that by the middle to late 1970s, after a new wave of students have come in, dreaming of particle physics, studying particle theory, but now also formally studying general relativity and cosmology and astrophysics, new textbooks being written every year to supply the need, that they start asking questions at this sort of interface between high-energy theory and cosmology. A field called particle cosmology is really kind of amplified. It's not created from scratch, but it really gets its institutional foothold as a kind of unintended consequence of this really kind of macro-scale shift in funding priorities and geopolitics. A
little bit of making lemonade out of the lemons that we were given, right?
That's right. And from that we get, now you and I can tick off our favorite successes, but we get a whole kind of amazing set of ideas about where our universe came from, where it might be going, what are the constituents of matter, and how can we test them. There's a whole set of questions that people weren't even posing.
Right, and
before.
So just the legitimacy of asking these questions appears.
That's right.
Even if we don't yet know the final answers to any of them.
That's right. No, you and I know, but
I'm keeping that for a future podcast.
Exactly. That's right.
Yeah.
Stay tuned.
And a lot of what is now that we're in the present era in the discussion, there's this whole new thing of asking for money from entities other than the government.
That's right.
Asking for private money, and if rubbing shoulders with the government and their secrecy and warlike predilections was problematic, asking for money from private individuals is problematic for a whole new set of reasons.
It certainly is. And so there's a middle buffer.
As we know here at MIT.
As we know at MIT
example.
with greater seriousness than we should have known earlier. Now it's inescapable. That's certainly right. And it's leading to, overdue, a real moment of real soul searching. And I use that, I really think it's soul searching here on campus. It's not going to go away soon. It's a real serious concern, a legitimate concern. But there's a middle path as well, where it's not just individuals who, as we know, can be sort of remarkably problematic, but also
and also, to be fair, remarkably generous and helpful.
Absolutely,
yeah,
no, that's certainly
it's
true.
The spectrum.
It's the spectrum. It's the full range, or it's not the full range. It's the range of human foibles among very rich individuals. So it's not the full range of humanity because most of us aren't that wealthy, but it's the range of the kind of human, complexities. That's right. And in between, there's a kind of buffer zone now, which I think is more substantial in terms of both supporting numbers of researchers and just the flow of dollars, which are private foundations or philanthropies. And again, there's a kind of irony or surprise here. So a growing proportion of research in our own field and many neighboring fields is supported by private dollars, and that often means now foundation money. In addition to federal sources, National Science Foundation or other agencies. The irony is that's in some sense a return to what had been a model in the United States in the 30s. 1920s and 30s.
Or in Italy in the 17th century.
Or indeed. That's right. We're all Galileos now. We're all seeking our de Medici. But unlike seeking an individual, Cosimo de Medici II, who might have been, quirky, we're now seeking in some sense, the foundation based on de Medici's, tax haven for his family or whatever it might be. We're seeking it from a slightly more institutionalized, slightly more stable structure of private money than the foibles of an individual. And again, something I've looked at historically in the 70s. There was again a turn to private donors in the face of this interruption of federal cash. And there it was often, in the instances I looked at, it was often quirky individuals who were often extremely generous and well-intentioned by many measures, but it was also not sturdy. Their personal situations could change.
Exactly, yeah.
Their money, they could die, and the family could disagree on how to spend it more. If it wasn't sort of an endowed gift, it was a recurring gift, but not permanent. And the amount of money was often just frankly not nearly the same. The actual dollar flow was not the same. And so we have that now, of course, sometimes with just horrible effects, not always, sometimes with wonderful effects. But there's a sort of slightly more institutionalized range of the foundation, which often uses something like peer review, often has a kind of buffer between the wishes or aspirations of the donor and the researchers. So it's not that, people who get money from the Ford Foundation have to improve, Pintos, right? There's a way of working out something like an intellectual autonomy, or at least something approaching that, which is much harder to work out with an individual writing you a check.
Yeah.
And it can be more money, and it can be a little more stable.
I mean, I have very mixed feelings about the whole thing. I mean, someone like Jim Simons, the founder of Renaissance Technologies, one of the world's most successful electronic trading firms,
right.
Has done an enormous amount for science, and enormous credit to him. Not only funding scientists, but also publications like Quanta,
That's right.
the magazine, which is probably the best science magazine
it's terrific.
existent right now. But they're individuals, and their primary allegiance is not to the greater good. They have their quirky individual things. There's the Templeton Foundation.
Right.
John Templeton was sort of the British Warren Buffett, but he also really wanted to reconcile science and religion, and that rubbed some people the wrong way.
Yes,
and so there's choices that people make, and there's a lot. This whole searching is going to have to keep going on for a long time when big institutions like our universities decide, when is it worth the money? Where should we hand things over? And it's not just science, right? The Koch brothers give money to economics and law schools, et cetera.
Absolutely. No, that's right. And so in some sense, our generation has to face this. It's not actually a brand new challenge. It is a kind of, in some ways, return to what had been taken for granted, less than 100 years ago, just in the United States, let alone in other times and places. MIT itself has gone through these waves. Just kind of parochially in my own backyard. We're now basically 100 years past what was called the technology plan here at MIT, the tech plan, which was first introduced in 1919. MIT had a president, Richard McLaurin. He was a Cambridge-trained mathematical physicist, though he had no practical knowledge. But anyway, he was university president for us here at MIT. And coming out of the First World War, MIT's finances were a mess, and he said we need cash, right? Research and teaching is expensive, so he says we will actively cultivate relationships with local industries. It was a school of technology, after all, and there were lots of Boston area manufacturing firms. And so the idea that kind of makes sense, sure, public-private partnerships or higher education with local industries, sure, but a generation in. 15 years later, many faculty on campus, including many engineers who'd been very involved with that project, had a kind of reassessment. Maybe more 10 to 12 years later. And they said, we'd gone too far, that the faculty, it was later determined, had given away too much kind of direction of research, too many restrictions on who could publish what, who was calling the shots of what would be studied and who could know. And we have to change, we have to insert more buffers for a kind of space for academic exploration that's not so closely tied to the whims of generous nearby partners, like in this case, private industry. So that's roughly 100 years ago. Roughly 50 years ago, we had another moment of real reckoning here at MIT.
It's amazing just for you to say that it's 100 years ago, because it could have been yesterday.
It could. If some of it feels very, very current. That's right. So roughly 50 years ago, in 1968-69 at MIT, and indeed at many other campuses across the U.S., we had a different sort of reckoning. Faculty and students and staff and community members more broadly. What's the role? Why is the Pentagon paying for such a high proportion of the research on campus with, again, what seemed like inappropriate conditions or restrictions? And I mean like marches in the street. There are photographs in the archives of, local Cambridge police with their billy clubs and their riot gear clubbing, protesters, and some protesters taking swings. It was a real fight. Marching down to demand the divestiture of MIT from certain kind of defense-oriented laboratories and demand other kinds of changes in academic governance and who gets to say who's going to do what project and who can share it. So we have these sort of moments. Roughly 100 years ago, it looked like private money is the way to go, including in particular kind of industrial money. 50 years ago, up until 50 years ago, it was simply beyond question. Of course, it's federal money. That's now the clean money, so it seemed, until that seemed really, really not so clean in the midst of the Vietnam War and these other very serious concerns. And so we have these kind of pendulum swings between whose money is seemed sort of obviously the way to go, what kind of money. And we haven't found, threaded that needle yet, not successfully.
And one of the extra issues with private money is sometimes that it's the rich get richer kind of effect. Yes. Like they want to give money to the sexiest, most glamorous subfields or whatever,
That's
or
right.
researchers or universities.
Yep. It's a version of that too, where even if we don't think about very, very wealthy individuals, it comes up now in sort of crowdfunding for science too. I get asked about this a fair amount by journalists who are writing about kind of Kickstarter-like campaigns or Patreon-type campaigns for science. On the one hand, it's like, wow, what a lovely idea. I mean, it appeals to me. It means that some large number of ordinary people are excited about science, so excited they'll actually put some of their own cash behind it. Who could not love that?
By the way, we have very generous Patreon supporters for the Mindscape podcast. I love them with the bottom of my heart.
I'm a giver through Patreon to individual artists and creators. No, it's not to knock the platform, but as applied to kind of university-based scientific research.
It's hard to see how it could possibly fill that role in any substantial way.
On the one hand, the volume, I think we're not going to build an SSC with that, for better or worse, or other large things. But also, how much of that's going to be driven by kind of the quirks of social media fandom. Who the best, slickest YouTube promotional video might attract more clicks, more likes. We don't have peer review with all the frustrations and flaws of peer review. There's at least a process. There's at least something like a procedure to try to rationally allocate funds. Not perfect, right? But it's at least a structure. Crowdfunding is like, hey, that looks cool, click. And so I have other concerns about other ways to engage, let's say private sources of funding, even with, again, what I would think would be wonderful intentions. That's not going to get us, that's not going to bring us to the promised land either.
No. Well, okay, good. So just to wind up then, what will bring us to the promised land? How should we be thinking if we're sort of medium-term thinkers here?
Maybe it's just a mushy kind of milquetoast answer, but I think we have to have some combination. Like, how could we not? And I think that not only for, let's say, political reasons, a kind of drawing from many kinds of sources and therefore many kinds of motivations, but I think, physics has suffered more than once in recent years, in living memory, from being hooked on a kind of monoculture, on a single kind of source, because that source won't last, to infinity. It might last over decades. Sometimes it'll last much shorter, but it certainly doesn't. A single element in the portfolio is not the way to go. So with something like with our eyes open to buffers, peer review, academic freedom to publish, with those kinds of controls or conditions really laid out in advance, then I think we can hopefully nudge toward a model that has federal input, maybe state and local, governmental inputs, some kinds of foundation support, some kinds of private industrial support, maybe some carefully vetted individual generous donors as well, and maybe that's the way to fill out a sustainable program. And we might not get to build the next SSC that way, but we hopefully could train a lot of really, really smart students in the meantime.
Well, and the other thing, I think you are going to agree with me on this one, so we're all preaching to the converted here, but physics, the rest of science, the rest of academia could do a little better job of making their case broadly for the importance of what they do.
I think that's exactly right. And the importance can include things like really important contributions to the economy. Think about the consumer electronics market. Where would that be without basic research in a host of fields? Physics, chemistry, many fields of engineering. Sort of curiosity-driven research that has led to what we now take for granted every day. So clearly some of it will be spin-offs, applications, a kind of better living through chemistry, if that phrase weren't so difficult to say with a straight face. But it also should be something about what makes us, curious people. What's part of our human, quest to know who we are, where we are, and what's coming. And I think that needn't be tied to a short-term goal. And there has to be space. There has to be some balance, some space to say we need really open-ended curiosity. We need to be able to support that, even if it won't make us better widgets in the next quarter.
You're singing my song. That's the perfect place to end. Thanks you. David Kaiser, thanks so much for being on the podcast.
Sean, it was a real pleasure. Thanks.